1891, Pennsylvania Lumber Yard. The veteran locomotive engineers gathered at the Clearfield Roundhouse couldn't contain their laughter when the flat car rolled in, carrying what looked like a mechanical insect compared to their massive consolidation locomotives. The Shea Class B sat oddly on its trucks, its 3 vertical cylinders mounted on the side like tumor growths, gears visible where proper connecting rods should be, and a boiler so small it barely seemed capable of making tea. "That's supposed to haul timber?" Jack Morrison spat tobacco juice toward the siding where workers were unloading the peculiar machine. Morrison had been running heavy freight engines for 15 years, and nothing about this contraption suggested it belonged on rails. The thing weighed barely 18 tons, less than half what his consolidation tipped at the scales. Its driving wheels measured a comical 33 inches, suitable perhaps for a child's toy train, but absurd for serious railroading. Shea's arrival at the Elk Run Lumber Company had been preceded by letters from Lima Locomotive Works, promising revolutionary performance on grades where conventional engines struggled. The company's operations manager, Thomas Hendricks, had invested $4,200 in the machine after conventional power had stranded 3 loaded timber trains on the mountain approach grades in a single month. Each stranded train represented thousands of dollars in lost production, while crews doubled locomotives or reloaded timber onto lighter consists. But the engineers saw only an expensive mistake sitting on the siding. Everything about the Shea violated fundamental principles of locomotive design that had been refined over 60 years of railroad operation. Steam locomotives derived power from large driving wheels connected directly to pistons through rigid connecting rods. This achieved maximum efficiency by converting piston pressure directly into rotational force without mechanical losses. The Shea's geared transmission represented heresy, using chain drives and universal joints like some oversized industrial machinery rather than a proper locomotive. The mechanical complexity alone guaranteed higher maintenance costs and frequent breakdowns. Those exposed gears would fill with sawdust and debris from lumber operations, grinding themselves into expensive scrap metal within months. Morrison climbed into the Shea's cab with several colleagues, eager to confirm his assessment of its inadequacy. The boiler gauge showed pressure capability of only 180 pounds per square inch compared to the 200 pounds his consolidation developed. The cylinder bore measured a mere 10 inches. His engine displaced 20 inches. Every specification reinforced the conclusion that Lima had sent them a fundamentally underpowered machine dressed up with complicated gearing to mask its deficiencies. "Hendricks wasted $4,000 on this contraption," Morrison announced to the assembled engineers. "Mark my words. This gear-driven disaster will be parked behind the maintenance shed within 3 months, and we'll be back to doubling consolidations on the mountain grades like sensible railroad men." The Shea sat silent under a light rain, its odd proportions making it appear even less impressive as water dripped from the external gearing. No one present could have predicted that this mocked machine would revolutionize an entire industry. The Allegheny lumber country presented operating conditions that challenged every assumption about steam locomotive capability developed on comparatively level mainline railroads. The timber stands that fed Pennsylvania's sawmills grew on mountainsides accessible only by temporary track laid directly up slopes that surveying crews measured at 8, 10, sometimes 14% grades, inclines where conventional locomotives lost traction long before exhausting their boiler capacity. Elk Run Lumber operated 42 miles of logging spurs extending from their Clearfield mill into the mountain forests. The main production spur climbed 1,700 feet elevation over 6 miles of track, averaging a 5.4% grade, with individual sections reaching 9%. Standard consolidation locomotives could haul approximately 15 loaded timber cars on level ground, but on the mountain grades, that capacity collapsed to 3 or 4 cars, depending on rail conditions and weather. The mathematics of grade resistance destroyed locomotive efficiency through physics that no amount of engineer skill could overcome. Each 1% increase in grade required roughly 20 additional pounds of tractive effort per ton of train weight to overcome gravity's pull. At 6% grades, a 40-ton timber car required 2,400 pounds of force just to prevent it from rolling backward, before accounting for friction, curve resistance, or acceleration demands. The consolidation locomotives generated impressive starting tractive effort, approximately 35,000 pounds at 180 pounds boiler pressure, but that force became inadequate remarkably quickly as train weight increased. The rigid wheelbase of conventional locomotives created additional problems on the sharp curves that characterized temporary logging spurs. The long frames bound against curved rails, increasing friction and wasting tractive effort on forces unrelated to actually moving the train. Hendricks studied the operational logs with growing frustration. His consolidations were spending more time waiting at the bottom of grades for helper locomotives than they spent actually hauling timber. The helper service required maintaining additional locomotives, crews, and fuel stocks at strategic points along the mountain spurs, all overhead that ate into profit margins in an industry where timber prices were determined by distant markets beyond any logger's control. The alternative approaches all carried unacceptable costs. Reducing train loads to match locomotive capability meant more trips to move the same timber volume, consuming more coal and labor while reducing daily production. Installing switchbacks to reduce effective grades required extensive track work on temporary spurs that would be abandoned once the local timber was exhausted. Some logging operations used aerial cable systems, but these worked only where topography permitted appropriate tower placement. Most frustratingly, the consolidations possessed more than adequate boiler capacity and steam production for mountain operations. Their fireboxes could sustain pressure indefinitely on steep grades, but that power couldn't reach the rails effectively because the locomotives lacked sufficient adhesion weight on their driving wheels. A 60-ton locomotive might generate 200 horsepower of boiler output, but could only convert perhaps 40% of that power into useful tractive effort before wheels started slipping on grades. The industry needed locomotives that could maintain traction on extreme grades while negotiating sharp curves, operating conditions where size and weight became liabilities rather than advantages. Conventional locomotive design had reached its practical limits in mountain logging territory. Ephraim Shea had approached the mountain grade problem from a perspective no trained locomotive engineer would have considered, mainly because Shea wasn't a locomotive engineer. He was a logger who understood timber operations better than railroad theory, and his solution violated every principle taught in mechanical engineering programs. Shea's fundamental insight came from observing how sawmill machinery distributed power. Mills used geared transmissions to convert high-speed, low-torque input from water wheels into the slow, powerful rotation needed for saw blades. The same principle could transform a small, lightweight boiler's output into the tremendous tractive effort required for mountain railroading if the transmission could handle railroad service conditions. The Class B design that arrived at Elk Run represented Shea's third-generation refinement of geared locomotive concepts he'd been developing since 1880. The boiler sat offset to the right side of the frame, making room for 3 vertical cylinders mounted on the left side. These cylinders drove a longitudinal drive shaft running the length of the locomotive's frame, connected through universal joints that allowed the drive shaft to flex as the locomotive negotiated curves and track irregularities. Bevel gears at each truck transferred power from the drive shaft to the axles, and all wheels, not just drivers, contributed to traction. This meant the 18-ton Class B had all 18 tons available for adhesion, compared to conventional locomotives where only driver weight counted for traction. The mechanical advantage of the gearing allowed the small 10-inch cylinders to generate tractive effort equivalent to much larger locomotives. The engineering calculations revealed why the design worked despite its unconventional appearance. The Shea's gearing provided a 3.5:1 reduction ratio between cylinder speed and wheel rotation. This meant every pound of cylinder pressure produced 3.5 pounds of wheel rim force, multiplying the locomotive's effective power without increasing boiler size or fuel consumption. The vertical cylinder arrangement with their direct connection to the drive shaft eliminated the reciprocating forces that plagued conventional locomotives at speed. Horizontal cylinders drove connecting rods that pushed alternately forward and backward with each revolution, creating vibration and stress that limited how fast locomotives could safely operate. The Shea's rotating drive shaft eliminated this hammering, allowing smoother operation even though absolute speed capability remained modest. The flexible drive shaft with universal joints addressed curve negotiation limitations that hampered rigid frame locomotives. Conventional engines had their Cylinders, driving wheels, and frames locked in fixed relationships. On sharp curves, this rigidity forced some wheels to slip sideways while others tried to follow the curve radius, wasting tractive effort and accelerating wheel wear. The chaise trucks could swivel independently while maintaining power transmission, allowing the locomotive to follow curves that would derail conventional power. The exposed gearing that seemed so vulnerable to Morrison and other critics actually provided maintenance advantages for logging service. Mechanics could inspect gear wear visually without disassembly, and replacement required simple hand tools rather than the specialized equipment needed for conventional locomotive running gear. Lima Locomotive Works had designed the chaise specifically for harsh, remote operating conditions where sophisticated repairs were impossible. But these technical advantages meant nothing until actual operation proved the chaise could deliver on its promises. The Brotherhood of Locomotive Engineers had developed strict hierarchies defining prestige and professional skill based on the locomotives men operated. Passenger service engineers occupied the top tier, commanding fast schedules with precisely timed station stops. Heavy freight engineers held respected positions managing powerful consolidations and mallets that moved commerce across the continent. Switching engineers and industrial locomotive operators occupied lower ranks, handling work considered less demanding than mainline service. The chaise represented something worse than a lower-tier assignment. It was an insult to professional competence. Real locomotives required skill to fire properly, maintaining steam pressure while managing water levels and combustion rates across varying operating conditions. Real locomotives demanded experienced throttle management, understanding how to balance cutoff, steam pressure, and injector operation to maximize efficiency. The chaise simplicity, offended men who had spent years mastering complex machinery. Its small firebox required minimal firing skill. Even inexperienced firemen could keep the modest boiler supplied with steam. The geared transmission eliminated the precise throttle control that conventional locomotives demanded. Opening the throttle simply engaged the gears more forcefully. There were no subtle cutoff adjustments or careful management of reciprocating forces. If you're listening right now, help me prove something wrong. My wife said I wouldn't even reach 1,000 subscribers, but I believe stories about old trains like this deserve to be heard. Help me show her that these videos matter. Please subscribe to our channel and let's keep these old trains' legacies alive. Morrison organized opposition among the Elk Run engineer roster before Hendricks could assign anyone to operate the chaise. The machine represented dangerous precedent. If geared locomotives proved successful, companies might replace skilled engineers with cheaper labor capable of operating the simplified controls. The Brotherhood had fought for decades to establish engineers as skilled professionals deserving appropriate compensation, accepting assignments on machines specifically designed to reduce the skill required for operation threatened everyone's livelihood. The resistance extended beyond the engineer ranks. Maintenance supervisors predicted nightmare scenarios where the exposed gearing consumed their entire parts budget within months. The universal joints would fail under stress, leaving trains stranded in remote locations requiring expensive wrecking crews for recovery. The bevel gears connecting the drive shaft to wheel axles would strip their teeth under the tremendous forces generated on steep grades, creating catastrophic failures that might derail trains loaded with valuable timber. Track maintenance crews worried that the chaise-geared power delivery would tear up rails and accelerate track degradation. Conventional locomotives had predictable force patterns that track builders accommodated through proper rail weight and ballast depth. The chaise continuous power application through all wheels might create different stress patterns that would require extensive track reinforcement throughout the entire logging system. Financial officers calculated that the $4,200 purchase price represented only initial costs. The specialized gearing would require expensive replacement parts available only from Lima Locomotive Works, creating vendor dependence that would inflate long-term operating expenses. Conventional locomotive parts could be sourced from multiple suppliers or fabricated in company shops, but the chaise proprietary components eliminated competitive pricing. Hendricks faced internal pressure to cancel the chaise trial before wasting additional money on an experiment that experienced railroad professionals unanimously opposed. The machine sat on the siding for 3 weeks after delivery, while management debated whether to return it to Lima before anyone actually attempted to operate it in service. The decision to proceed came not from confidence in geared locomotives, but from desperation born of failed alternatives. May 1891 brought the operational crisis that forced Hendrick's decision. Spring rainfall had saturated the mountain grades, reducing rail traction to levels where consolidation locomotives couldn't haul even minimal timber loads up the main production spur. The company had 40 loaded timber cars staged at various points along the mountain grades, representing nearly $8,000 in cut timber that couldn't reach the mill for processing. Every day those cars sat on mountain sidings cost the company money while sawmill workers stood idle, waiting for logs. The consolidations physically could not move trains up the saturated grades. Morrison had attempted hauling a 4-car consist, the absolute minimum for economical operations, and stalled completely 3 miles into the climb, where the grade steepened to 7%. The driving wheels slipped helplessly on the wet rails despite sand application, unable to generate sufficient traction to overcome both grade resistance and the train's inertia. Helper service proved equally useless under the conditions. Doubling. Locomotives put more weight on the rails but didn't proportionally increase traction on the slick steel. The additional locomotive weight actually made curve negotiation more difficult, with both engines binding against the outside rails and wasting whatever traction they could generate. Some European railroads used rack and pinion systems for extreme grades, but installing such equipment on temporary logging spurs was economically impossible. Hendricks authorized the Shea trial with conditions that reflected management's skepticism. The locomotive would attempt hauling 4 loaded cars, standard minimum load for viable operations. If it failed, the machine would be immediately sold to whatever buyer Lima could find, and Elk Run would abandon the upper mountain timber stands as inaccessible with current equipment. If successful, the trial would be expanded to determine actual operating capabilities. Finding an engineer willing to operate the Shea required offering premium pay, equivalent to passenger service assignments. Robert Dutch Werner finally accepted, motivated partly by the extra money and partly by curiosity about whether geared transmission could actually work under railroad conditions. Werner had worked as maintenance mechanic before becoming an engineer, giving him technical perspective that pure operating men lacked. The trial run attracted an audience of skeptics who gathered at the base of the mountain grade on a gray morning where low clouds promised more rain. Morrison and 8 other engineers had bet a collective $240 that the Shea would stall before reaching the halfway point. Maintenance supervisors prepared wrecking equipment, anticipating gear failure that would leave the train stranded. Even Hendricks appeared uncertain, pacing near the mill office while the Shea built steam pressure for the attempt. Werner performed the pre-departure inspection with unusual thoroughness, understanding that everyone was expecting, perhaps hoping, for failure. The boiler pressure gauge showed 170 pounds, adequate for the small cylinders. The gearing appeared properly lubricated, though Werner remained skeptical about whether exposed chains and universal joints could handle sustained, heavy loads. At 7:15 a.m., Werner released the brakes and engaged the throttle. The Shea's vertical cylinders hissed as steam pressure built, and the locomotive began moving forward with a distinctive rhythmic clatter from the gearing that sounded nothing like conventional locomotive exhaust. The Shea's initial movement generated no dramatic displays of power. The locomotive simply started pulling and kept pulling. The 4 loaded timber cars, totaling nearly 80 tons, rolled smoothly away from the staging area as Werner gradually increased throttle. The geared transmission made a steady metallic rhythm completely different from the sharp exhaust bark of conventional locomotives, a sound that suggested industrial machinery rather than railroad power. The grade began its serious climbing 2 miles from the mill, where track surveying markers indicated 5.8% inclination. Werner watched the steam gauge carefully, expecting pressure to drop as the boiler struggled to meet increased demand. Instead, pressure held steady at 165 pounds, while the Shea maintained constant speed around 6 miles per hour. The small firebox was supplying steam as fast as the cylinders could consume it, with the gearing allowing sustained heavy pull without the pressure fluctuations that plagued conventional locomotives on grades. At the location where Morrison had stalled 3 days earlier, Werner actually increased speed slightly. The rail conditions remained treacherous. Recent rain had left the rails slick enough that conventional locomotives would be slipping wheels. But the shays, distributed weight across all axles, and the continuous power delivery through the gearing provided traction that defeated the slippery conditions. Every wheel contributed to pulling rather than just the drivers, effectively tripling adhesion compared to conventional locomotives where only driver weight counted for traction. The skeptical engineers watching from the base used field glasses to track the shay's progress up the mountain face. They could see the distinctive smoke plume, lighter than consolidation exhaust because the small firebox burned less coal, climbing steadily past landmarks where helper service usually became necessary. The shay was maintaining speed on grades where double-headed consolidation struggled, and doing it with a train load previously considered impossible for a single locomotive. The sharpest curve on the route, an 18-degree bend combined with 7.2% grade, had been the site of multiple derailments when consolidations tried to force heavy trains around the combined obstacle. The rigid wheelbase of conventional locomotives couldn't accommodate the curve radius without binding against the rails, and attempting to power through usually resulted in wheels climbing the outside rail or car couplers parting under stress. Werner approached the curve with apprehension, reducing throttle slightly while maintaining enough momentum to prevent stalling. The shay's trucks swiveled smoothly through the curve with the flexible drive shaft accommodating the angular changes. The locomotive maintained steady pull throughout the curve without the lurching and binding that characterized conventional power on sharp curves. The universal joints that had seemed mechanically vulnerable were proving to be genius engineering for logging service conditions. 2 hours and 40 minutes after departure, Werner crested the summit of the production spur with the 4-car train intact. The shay had climbed 1,700 feet through conditions where consolidations couldn't haul half the load. The locomotive's steam gauge still showed 160 pounds pressure with coal remaining in the bunker. The run hadn't even stressed the machine's capabilities. Morrison paid his bet silently, watching the shay through field glasses. That peculiar geared machine had just redefined what was possible in mountain railroading. Within 6 months, Elk Run Lumber operated 3 additional shay locomotives while the original consolidation sat idle except for valley flat switching duties. The economic transformation was immediate and dramatic. The shays hauled 8-car timber trains up grades where consolidations had struggled with 3 cars, tripling daily production from the mountain timber stands without increasing labor costs or requiring helper service infrastructure. The operational advantages extended beyond raw hauling capacity. The shays burned approximately 40% less coal per ton of timber hauled compared to consolidation and helper operations. The flexible trucks reduced rail wear on the sharp curves that characterized temporary logging spurs, cutting track maintenance costs by roughly 30%. Most surprising to maintenance crews, the exposed gearing required less servicing than conventional locomotive running gear. Mechanics could inspect and lubricate components in minutes, rather than hours needed for conventional valve gear. Word spread through the logging industry with the speed of forest fire. By 1893, Lima Locomotive Works had sold over 150 shay locomotives to timber operations across North America, with orders backlogged 8 months. The design that railroad professionals had mocked was revolutionizing an industry by solving problems that conventional engineering had considered insurmountable. The shay's success spawned competing geared designs, the Climax with its 2-cylinder arrangement, the Heisler with center-mounted drivetrain, but none achieved the shay's market dominance. Over the next 40 years, Lima would manufacture nearly 3,000 shay locomotives, in configurations ranging from tiny 2-truck machines weighing less than 20 tons to massive 3-truck monsters exceeding 150 tons for heavy industrial service. The impact extended beyond logging operations. Mining companies adopted shays for underground operations where their flexible trucks could negotiate incredibly tight curves. Industrial plants used them in steel mills, shipyards, and manufacturing facilities where conventional locomotives couldn't operate. Several short-line railroads operating in mountainous terrain replaced their entire conventional locomotive rosters with shays after discovering the geared machines could maintain profitable operations on grades where road locomotives required expensive helper service. The engineering vindication proved most satisfying for Ephraim Shay, who had endured years of ridicule from professionally trained locomotive designers. His pragmatic approach to mechanical problems, understanding that moving logs mattered more than conforming to railroad orthodoxy, had created a completely new category of locomotive. The Class B, that arrived at Elk Run as the object of mockery, became the first unit of a fleet that would transform industrial railroading worldwide. Morrison eventually qualified as a Shea engineer, discovering that operating the geared locomotives required different skills than conventional power, but no less expertise. The Brotherhood of Locomotive Engineers created special qualification standards for geared locomotive operation, acknowledging that the machines demanded professional competence despite their mechanical simplicity. The smallest steam engine the crews had mocked hadn't just outpulled everything around it. The Shea had redefined what small locomotives could accomplish, proving that engineering success came from solving real problems rather than following traditional design conventions. Sometimes the most revolutionary machines were the ones that looked least impressive sitting on the siding.